In this video, we're going to be talking about a very common application of derivatives, which is talking about position, velocity, and acceleration. These are also called, or this topic is also called straight line motion, and there are many facts about it, and let's take a look at some of these bullet points. Position is often represented by S of t. That tells you where a particle is located at a given time t. Velocity is basically the derivative of position. So notice it can be written as S prime of t, but sometimes it's written as V of t as well, V standing for velocity. That is, again, the rate of change of position at a given time. If velocity is positive, an object will either be moving to the right or up, whereas if velocity is negative, an object is either moving to the left or down. If velocity is 0, an object is at rest, or it's possible that for that split second, it's basically changing direction. Speed, which is the absolute value of velocity, is the rate at which position is changing, but it has no direction. Acceleration, that's the second derivative of position, or the first derivative of velocity. So we're going to say that that's the rate at which velocity is changing. Thinking about if you accelerate while you're driving a car. When velocity and acceleration have the same sign, the particle is considered to be speeding up. Whereas if velocity and acceleration have different signs, the particle is slowing down. So let's use our knowledge of position, velocity, and acceleration to answer each question here. So we're going to look at a few different examples. One is going to be here where we're given a function. In number 2, we're going to be analyzing a graph. And in number 3, we're going to be looking at a table of values. All right, let's take a look at number 1. A particle moves along the x-axis. Its position can be modeled by the function s of t equals t cubed minus 3t squared plus 6t plus 7, and time is greater than or equal to 0. If we determine the velocity of the particle at t equals 2, so the derivative of position is equal to velocity. So I'm going to take the derivative of s of t. That would give me 3t squared minus 6t plus 6. And if I want to evaluate that at 2, I'm going to plug 2 in every time we have a t in our function. And let's simplify that. So we have 3 times 2 squared, or 12, minus 12 plus 6. So the velocity of the particle would be 6. To determine the acceleration of the particle at t equals 2, the second derivative of position, or the first derivative of velocity, is equal to acceleration. So I'm going to take the derivative to our function from part A. That would give me 6t minus 6. And let's evaluate that at 2. And I get positive 6. So for part C, we want to know, is the particle speeding up or slowing down at t equals 2, and explain. That goes up to our notes up here. So velocity and acceleration have the same sign. We say speeding up. If they have different signs, we say slowing down. So in this case here, since they are both positive, they both happen to be 6 as well. So we are going to say that they have the same sign and then therefore speeding up. So I will write the particle is speeding up since velocity and acceleration have the same sign. All right, let's look at an example with a graph. Number 2, the graph below shows the velocity of an object v of t moving on a line over time t. Part A, over what interval of time is the object moving left? Well, that's whenever the velocity is negative, and I can see that that's happening on my graph between 7 and 8, and I'm going to use the open interval to represent that. Part B, when is the object slowing down? So this would mean that velocity, and we can write a little note here, velocity and acceleration, I'm going to abbreviate, have different signs. Okay, and we're going to explain that too. So let's analyze our graph here. velocity is given to us, so I can see here that velocity is positive. Velocity is positive, velocity is positive. I'm just going to look at each interval along the x-axis, and I see all of these values where velocity is positive, but over here, velocity is negative. Now let's talk about the acceleration. That's the rate of change here of this graph, the rate of change of velocity. So over here, the rate of change, or the derivative, is 0. Here, acceleration's negative. Here would be positive because we see a positive slope. Positive. Acceleration is 0. Acceleration is negative. Acceleration is negative. And acceleration is negative. So we're looking for ones where we have opposite signs. So I can see that's happening over here, and over here. So those two at the end are consecutive, so I'll put that together. But it's slowing down. So I'll write the object is slowing down. Over. So we have the first interval between 1 and 2. And we have the second interval between 5 and 7. And I'll put our answer from before, that this is because velocity and acceleration have different signs. C, at what time t is the object changing direction? So first we should look for when velocity is 0, but then we also want to make sure that we are changing from positive to negative. So if I look at the graph at t equals 7, the velocity is 0, and we can also see we go from positive velocity to negative velocity, so that means we're changing direction. If you were also looking at t equals 2, yes, that object has a velocity of 0 there, but we are not changing direction because velocity is staying positive. So for C, I'm going to say that's at t equals 7. And D, we've already somewhat addressed, but it says over what interval of time is the velocity increasing? That basically means our acceleration should be positive. Okay, since acceleration is the derivative of velocity, we're looking for the intervals where we have positive acceleration. So we all have those notes on our graph already. So I see here acceleration is positive, and that interval is going to be my answer. So that's between 2 and 4. All right, for number 3, we're going to look at an example with a table. So it gives us the velocity in feet per second of a particle moving along the x-axis, and it tells us the velocity function is differentiable. All right, for part A at t equals 0, is the particle moving to the left or the right? Explain. So we're taking a look at this part of our table here. So I'm going to say at t equals 0, the particle is moving to the left, because the velocity is negative. B, at what value or values of t is the particle at rest? That's at t equals 6 because we can see that the velocity is 0. For C, we're going to approximate v prime of 4. So 4 in our table would be here, right? So if I was trying to approximate what that would be, the rate of change at 4, I'm going to use the two surrounding values to find the slope, and we're going to make sure we include units here. So I would have 0 minus 2, change in y values, over 6 minus 3, change in x's. So this would give me negative 2/3. And for our units for velocity were feet per second, but we're finding the rate of change of that, a rate of change of velocity, derivative of velocity. So it's going to be feet per second, or you could say feet per second squared. And for part D, is there a time t equals c guaranteed such that the velocity of c at c is negative 3 in this interval 0 to 17? And we're going to justify our answer. So if we go to our table of values here, we're basically trying to understand and see, could there be a value of t where the velocity is -3? And I'm going to just erase this a little bit here. But if I had to guess, I could imagine that somewhere in here, the velocity would be -3 because I can see it's gone from -6 to -1. But in order to write this, we're going to have to talk about the fact that this is a continuous function and how we know this. So the first thing I'm going to start off by saying is that since the velocity function is differentiable, it is also continuous. That's because anytime we have a differentiable function, we know that it is continuous. Differentiability implies continuity. Then I'm going to talk about since v of 0 is equal to -6 and v of 1 equals -1 by the intermediate value theorem, there must be a value c where v of c is equal to -3. So again, to recap that answer, since we know the function must be continuous and we're going from the output of -6 to -1, we have to pass -3 along the way, and that's according to the intermediate value theorem.